Hey. So, all right. So we'll start again with Chiara Camere talking about finite group actions on hyperkähler.
Thanks for your organizers for organizing this nice school. I'm happy to be back in Bonn. So the aim of this course will be two different aims actually. So on one side I want to describe the very basic general theory to study finite group actions on irreducible holomorphic symplectic manifolds. But on the other hand, then I want to go to applications. So I will focus on application also to the study of quotients actually. So I will have the following structure. So let's say that in today and tomorrow we will see, well, first of all, the basics for automorphisms of irreducible holomorphic symplectic manifolds. I know I use hyperkählers in the title, but then that's what I'm going to call them. And this is and then we're going to say how we can study an automorphism of P1. How can we study it and its properties? And what its existence implies for the geometry of the underlying manifold. And we will give some hints how one can address the problem of classifying group actions, finite group actions, existing on a deformation family. Well, the group action will be on the singular manifold, but let's say which kind of group action has given the formation family I have, depending on the choice in the family. This should be today or tomorrow, hopefully. And then, second half of the week, we are going to see, well, more specifically, the case of symplectic involutions on orbifolds of K55 and the construction of orbifolds of Nikulin type. Here we are getting out of the class of smooth irreducible holomorphic symplectic manifolds. As this suggests, these are orbifolds, which is much more a recent topic. We will discuss that in the second part of the video. So, as a motivation, we mentioned that the study of automorphism of irreducible holomorphic symplectic manifolds and of finite group actions has been started since foundational work of Nikulin and Kai on K-free surfaces. Most of the things that we studied on irreducible holomorphic symplectic manifolds originated first in the K-free surfaces case, and then by Bodin, Fujiki indicated of higher dimensional irreducible holomorphic symplectic manifolds. So here we are around the 70s, 80s. But of course, it's interesting to study automorphism. That's what geometry does, take a manifold and study its symmetries somehow. But it's not only for that here people were getting interested. It was also because in some cases, here the quotient of a K-free surface for certain kind of automorphisms are again K-free surfaces. So at the very beginning of the theory of irreducible holomorphic symplectic manifold, they immediately looked if there was a way of generating new deformation families by taking quotients by finite group actions. That was the first motivation historically, I think, to start the study of automorphisms on irreducible holomorphic symplectic manifolds. Unfortunately, that's not the case. The dimension grows and you often get singularities. So you lose smoothness. Okay? And then from there, a lot of work is started. As a choice, I will mention a little of K-free surfaces, but not really the complete results. It's a huge amount of literature over finite group actions on K-free surfaces. And I will try to focus on this. Actually, the title is more general of what we will do, so maybe I should make already a decision. So, as it comes to examples, we will discuss mainly manifolds of K-free and type. There is a lot of work on the other deformation families. It is very interesting, but K-free and type is the one on which I worked, so that's why I'm presenting examples I know the best. Okay? And the other thing is that we only have 4 hours. We will discuss the building blocks of finite group actions, which are cyclic groups, mainly of prime order. Okay? So that will soon become our assumption. Okay? Here, well, I will even go easier and go to order 2. So the easiest finite group that we can find. That's what I want to say. Okay, let's start warming up with examples of these actions. Let's see. Well, I think that the most famous example of automorphism I can claim that we all know at the beginning of the study of algebraic surfaces is take T2, because move sets taken slightly. When I put the number below is the degree, okay? So this is move. I consider the double cover of P2 branched along this subset. We obtain an S, and I guess you all know that it is a K-free surface. Okay? S is a K-free surface. It's not difficult to write this equation, actually. It's going to be something like this. Okay? And there is an involution because we have a double cover, active mass. I. So what does it mean? It's just extending the sign of that. That's very explicit, and its fixed locus is isomorphic to our system. Okay? So now the statistic is moved. Okay? And as I said, we all know this example of involution. It will be non-symplectic, as we will see. That you can, from the things that we will say little by little, the easiest way to deduce is just by the fact that the fixed locus is one dimension. Okay? So this will be non-symplectic. I will explain all the terminology, of course. This is just introduction. Now, let's degenerate a little our conic. If we want to go and look for richer geometry. Okay, so we're again in P2. Let me put it here. But instead of a smooth conic, I'm going to take the intersection, or the union, sorry, not the intersection, of a quadric and the conic. Yeah, right. I know that it's difficult to have both of them. Can you read a little better if I read like this? Okay, so these are smooth quartic and smooth conic intersecting transversally in 8 points. Okay? Now, we can do many things with this. So, we can consider the double cover here. Our double cover will be singular now, because the branch is singular. And it will be singular over the 8 points of intersection that we have here. Okay? And here we have y, which will be singular. It's a singular K-free. We solve the singularities, you obtain a K-free surface. And we can even go further and consider another double cover, which will be again a K-free surface. It's easier to see the construction of S, not this way, but in this way. So I can of course consider other two double covers of P2. I can branch only on C4 or branch only on C2. Okay? So if I branch only on C2, so let's say that here you have the branch C2. What I obtain, well, it's a quadratic, right? And if you look and go back, you see that your C4 becomes something of B degree 4, 4. Okay? Now here, if you branch along C4, what you obtain, and probably you need to think a little more about it, that it's a del pezzo of degree 2. Okay? And if you now look for the image, the inverse image of the organic, what you obtain is gamma 3, genus 3, which will our second branch. So this will be this, which will be the first branch, will be inside minus twice the anticanonical, which tells you that now, if you take the second double cover, branched along the one here, or of Q branched along the one there, so the two before, what you obtain upstairs is a K-free surface. Of course, this diagram you don't have always. You need that this one is invariant for the exchange. Gamma is invariant for the exchange of the two P1. Okay? We have plenty of evolutions here. If you go looking at our K-free surface. Okay? Because we have plenty of double covers. So, on S, it's clear that it is K-free because it's the second branch is regular and minus twice the anticanonical, okay? So when you go upstairs, you get trivial canonical. On S, we get involutions. Let me call them with the name of the quotient. Okay? IQ is involution such that S quotient is by IQ is K. Sorry, I put the other way around in my notes, so I'm going on the wrong side. Okay? Then we have I of the pets, producing the pets of the D2, and then we have IY. But it's nice and visualize if you want to compute the pixel loss. This is going to be 8 points. And this will be, of course, isomorphic to the two branches, right? Yes. So you see that there are differences between these pixel loss, eh? And this will tell us, this already tells us that the action is different. So it's really obscure right now what you can deduce from these, but that's how you start a study of a group action. Yes?
Would you just repeat one more time the maps in the middle of the diagram?
Yes. The fact is that I didn't want to give the details here because it's very complicated to express. So let's say that I'll do this way. So I consider S, I'll define it as the B double cover of P2 in the following two branches. So first you do double cover over a small conic and you get to a quadric, and then I don't want any of these double covers. I want to impose that what I obtain here is symmetric with respect to the exchange of the two P1. That's a further condition, okay? I'm not taking the most general. And then I'm doing the double cover branch of gamma 4, which is the inverse image of C. Okay, in this way I obtain a K-free surface, but this symmetry here lifts up, and the Y is the quotient of that symmetry.
Thank you.
So IY is the lift of the exchange. So that's less easy to see. Okay?
So what happens in this more general case? You just lose this information, or but the other one will still be there. The other one will still be there.
No, in fact, so this picture you have when you have this, so you can have only one side and not the other. Okay, but in the case it will be more general. In fact, the existence of these evolutions, both of them, the three of them actually, gives you that the Picard rank here is higher than you would expect. Okay? If you just go, let's say, this way, the capsule degree 2 is to blow up of between 7 points. So its Picard rank is 8. Okay? You get the ample plus and the 7 exceptional divisor, which is the same you would expect here. But this K-free surface with all this group action, which is bigger, okay, has Picard number 9. Okay? For reasons I cannot tell you now. I hope I have the time to come back to this example. Otherwise, it's well explained in the literature. Okay, it's in Van Gemen's article, if you want a reference for that. For Nikulin evolutions. Okay? So, as I said, everything is going to be quite obscure right now, apart from the computation of the double covers, which you should do using the theory of the light surfaces, but that was just to say, you see there's a lot of geometry you want to understand here. And we need tools to study these automatisms, relate them, and understand them. Okay, that was only the upshot of the warm-up that I wanted to say. And also, yes, say maybe that.
Excuse me. One of the things is the resultant surface, I mean, S is a K-free surface.
Branching of a rational surface along the curve, which is minus in twice the anticanonical. So if you use double cover formula, you see that you obtain something trivial with trivial canonical bound. Okay? Good.
Sorry, I'm asking, how general is this fact that you can has two irreducible components, then branch in different order to get the same thing?
Okay. The thing is, you can degenerate this in every way you can think of. Not even just two reducible components, even to 6 lines. And you get more, let's say, K-free surfaces with higher and higher Picard rank. So this specific group action is here, it's special for this K-free, but you have similar pictures that you can construct depending on how your static becomes singular. Okay? That's the way of actually generating many symplectic evolutions on K-free surfaces. Not all of them, you can obtain like that. Okay? Alright. That was the introduction. Now let's start explaining things. So as I'm the first speaker mentioning them, I guess I need to give at least a quick introduction to reducible holomorphic symplectic manifolds. at least to fix the notation. Okay? As a choice, I won't give any proof about irreducible homomorphic symplectic manifolds themselves, only about properties of connectivity. Otherwise, 4 hours would have been enough to get 20 minutes. And now you'll see, I don't teach in Germany usually. If the erasing is too bad, just tell me. I'll try to. All right. So, irreducible homomorphic symplectic manifolds. First problem. Well, first of all, let's put the definition once and for all on the blackboard. So, a compact scalar manifold X is irreducible holomorphic symplectic. Let me write only once. Well, almost right. If it is simply connected and if the H20x is spanned by what we call a symplectic. There are two possible notations for the symplectic form, either sigma x or omega x. I usually use omega x, and the people will use the other one, but I think the audience will adapt. Okay, so where omega x is symplectic holomorphic form, symplectic means everywhere on the thin, right? Symplectic holomorphic. Okay. The existence of this form gives strong properties about the geometry of this irreducible homomorphic symplectic manifold. So first of all, its high power trivializes the canonical bundle. So these are manifolds with trivial first-term class properties. But even before, the complex dimension of an irreducible homomorphic symplectic manifold is always an even number, because you get the symplectic form on the tangent space at any point, and the symplectic space, vector spaces have even dimension. Okay? Second, A of x is trivial, so C1 of x is 0. These are part of the building blocks in the Bogomolov decomposition theorem, together with Toroi and Calabi-Yau varieties. Moreover, the symplectic form, now I should be careful about, this will be the tangent bundle for me. It gives an isomorphism with the Schiffer differentials. And you can actually compute these numbers, and they are either 1 if p is given, in the reasonable bound, okay? Between 0 and 1, and 0 otherwise. As a consequence, h on 0 is equal h01 is equal to 0, and this implies that any irreducible homomorphic symplectic manifold as first Betty number equal to 0. Okay? We don't know, so there are examples of non-vanishing odd Betty numbers, but they are not for the one. What about the H2? I think I should start dividing the blackboards in two.
Just a little question before you erase. Do you mean that these involutions generate a group C mod 2 plus C mod 2?
Yes, they are commutative.
Okay, thank you.
Okay. So let's start with this so that this is better. Another important property, which we use a lot, actually, I had a problem in numbering, as you know. That was 4. There exists an undegenerate quadratic form in the homology of X. This is the so-called Bovil-Bogomolov-Fujiki. Okay? For me, it won't be important to give the exact definition of it. Let me just mention that it is related to intersection theory of manifold, of course, and which satisfies Fujiki relation. And yeah, so there exists a constant, Fujiki constant. These are two forms. So you have to take the top set intersection, take the dimension of each two, and you want to put the same here as well.
I think on the right hand side, it should be good.
Yes, you're right. Thank you. So here it is. Yes. Okay. So we have a lattice structure, and this lattice structure actually controls a lot of the geometry. It's quite surprising actually, because these are in general 2 n-dimensional manifolds, and you can deduce a lot of their geometrical properties by studying H2 and top. Okay, then for more deeper things, you need also higher degree homology, but there's a lot of information which is included in there. So H2 ZQ is what I will call L, or if there is any doubt, Lx. Okay, but I will omit X if it's clear what I'm talking about. And it's a lattice, an integral lattice of signature P. This comes from the fact that from the definition that I haven't given, Q is positive on the symplectic form, on its conjugate, and on a Kähler form. That's how you prove it. Okay, so you get a three-dimensional positive subspace spanned by omega x, conjugate of omega x, and the Kähler form. Not only this quadratic form, the A swell is compatible with the whole structure. Okay? So the Hodge decomposition is over to the complex. H0, 0, 2, H1, these two pieces are orthogonal. Okay? And this in particular with respect to Q. And this in particular implies that the Néron value of x, for the Picard, which is the same in this case for this manifold, is you can describe it or it's defined as this intersection, right? And this you can describe as the orthogonal to the symplectic form intersected with the integral part of the commodity. Okay, that's a very convenient way of describing the Picard, the Néron. In particular, this will be the period of our manifolds. I won't discuss periods today. I'm splitting the summary about reducible homomorphic symplectic manifolds in 2 episodes, and we're going for the more difficult properties like Torelli and modular spaces tomorrow. But for now, we have this. Okay? Anything else I wanted to recall today? So in particular, Kähler classes are orthogonal to the symplectic form. Okay? Kähler classes will sit inside here, so they are orthogonal. For any Kähler class, so this will be my notation for the Kähler clone of X. This will be the bilinear form associated to Q. Okay, I won't use the B, I will just use parentheses. Or a Q to enter inside. And finally, what I wanted to recall today before finishing this list of properties is Hilbert's projectivity criterion.
What was Max was the numerical?
Yes. No worries, I said just said they should have written. Okay, yes. Okay. The curly case. It should be bigger than normal case, but well. If you have a doubt, just ask. So this is telling us, this in general will not be algebraic, okay? There's nothing algebraic in the definition. And in fact, the very general one will be non-algebraic. But this criterion is telling us how to identify projective ones among them and where they are projected if and only if the Néron inside our lattice is hyperbolic sublattice. Hyperbolic meaning signature is equal to 1. Equal number 1 as well. Okay? It's always a primitive sublattice. It is projective if the Néron is hyperbolic. So the signature is one. I'm just saying, so one implication is pretty clear. So there is a, if it is like this, there is an ample class because it's scalar. We have a class on which positive, the 4, and it's integral. So it's okay, the other one is way more complicated. Okay, so that was all I wanted to solve for today. As I said, there are deeper properties we will need, but I decided not to talk about, just not to make a huge summary for the full course, but discuss also homomorphism. Before, let me mention fixed notation, for example, to use. We have already seen K-free surfaces. They are the only reducible holomorphic symplectic manifold of dimension 2. Okay. You can generalize this to obtain a family in any even complex dimension by using Hilbert scheme for Lloyd spaces, according whether you consider projective or not. Hilbert schemes of endpoints on K-free surface. So the fifth K-free surface is S. The Hilbert scheme of endpoints I will denote by this. Okay. Let me roughly recall how you can construct it. You can start from the self-product of the K-free surface, quotient by the symmetric group, and produce the symmetric product of the K-free surface. This is singular, of course, and it's singular along what we call the big diagonal. Yeah. Let me not be so precise. You can resolve the singularities here via the Hilbert formula, and what you obtain is the Hilbert field. Okay? So, you have just one exceptional divisor over here, which tells you that the second Betti number of this is nothing else than the second Betti number of your K3 plus 1. Here, I didn't recall, but B2 over K3 is 22, and here we get 23 as the second Betti number for all dimensions to n. Okay? In fact, let me recall that the lattice here is exactly the lattice we studied in the theory of surfaces. It's unimodular. And it's three copies of the hyperbolic plane. Okay, so this one has this quadratic form, and two copies of the negative definite root lattice associated to the dinking diagram here. So now I want to say more about the quadratic form, explicit quadratic form, but that's how it is defined. Here, the intersection theory, what you miss is the offset intersection of your exceptional divisor, and then computing its quadratic, doing the quadratic form, okay? And what you obtain is in fact that if this lattice splits as the embedding of the lattice of the K3 you started from, orthogonal direct sum is this, and the quadratic form, and can be described like this. Intersection theory tells you that it's not E, of course, it's half E. That's why Christian was puzzled. half. So delta is half the class of deception device. Okay. Oh,
You have n plus 2, n factor 2.
yes. Thank you. Otherwise, we will start with a contradiction in the first point. Yes. Okay. Annotation. Any irreducible. So these are elements in the deformation family. Okay. But not all the deformations are Hilbert schemes of K-free surfaces. The reason, which will be more clear when I record the modulus theory, is that here you have a 22, here you get one more direction in the deformation family. So not all the complex deformation of these Hilbert scheme of points are Hilbert scheme of points of K-free surfaces. I will denote like this. If any irreducible homomorphic symplectic manifold, which is in the deformation family. Examples which we will use are modular spaces of sheaves or of twisted sheaves but hopefully before I need Van Daniel will have introduced them so that I don't need to. Let's see. Let's wait for it. I'll wait now. Or given a smooth cubic orbifold, simplified, you can consider the fun variety of lines contained in Y, and this is of K-free to time. So this will be a free n for any dimension. Here you obtain a fourfold. Let's go build an Aggie result. We will use to see some examples of automorphism. Okay, then there are more deformation families, and I just want to record the mentioning that, as I said, I want constructive examples that are really important. It's not that they are not important or not well studied. Okay? So we have generalized Kummer manifolds, and then two deformation families due to already, which are in dimension 6 and 10. For all of them, we know the lattice, the Bogomolov projective lattice, the Betti number, and even the Cauchy number. Okay. There are more projective models that we know, in particular in the family, the deformation family of K-free to type. We might come back to that in the second part of the week. Let's see. Now, so far for the summary on the irreducible homomorphic symplectic manifold, let's go to finite regression. Okay, so we want to study finite group inside X will be an irreducible homomorphic symplectic manifold. We want to take a finite group inside the homomorphism of X. So these are real more maps. And this is clearly contained in the group of Weber-morphic self-maps. Okay. So first remark that I want to do is that the dimension of the homomorphism group, we know that it is the H0 of the tangent shift. Okay? But we discussed this. So this is by the irreducible homomorphic symplectic manifold. This was isomorphic at the shift to the shift of differentials. So this is H01. X, and we said that this is 0. So the automorphism group is discrete. Okay, how do we study these automorphisms? I want now to introduce part of the definitions that I mentioned in the introduction, and first properties. So first of all, let me remark that we can look for the action of homology. Not on all homology, I will be interested on the H2, the action of the H2. So I will consider this isometry. Here it is an isometry. Okay? In fact, there is a map. We can even go from here also for binomorphic maps. Most of the duality of which I will recall tomorrow, it's about describing properties. You can rephrase as describing properties of this map. Okay? For now, let me insert two things. So, the image. The first thing, remarks. If you look at the image of the automorphism group, this will be contained. Well, it will be an odd isometry, in the sense that if you tensor with C, what you get is a morphism of odd structure. An automorphism has to be with odd structures, okay? So we are going here. That's true also for biomorphic maps. Let's say that, just to be quicker. Here, if it's an automorphism, it also fits characters. Okay? So there is this small k in the character. So the image is for sure contained inside there. That's not optimal. If I don't want to give all the full properties of irreducible homomorphic symplectic manifolds, we will come back and saying something more precise. But for now, it's enough to know this for us. So what I want to do to finish today. Second thing,
why does it fix the character? Why does it fix an element of the character?
I believe that automorphism preserves the character. You can check it, you verify it. That automorphism preserves the character. Not by
definitely
say they preserve a particular element.
Yes. I'll come back to that. Maybe the argument that I will give in a lemma will convince you of why. Okay? They have to fix, they can fix a color class. But if you want, we can stay more general here so that everything is good. And just say, yes. but nothing is not convincing. Okay? Second thing, was it the only question, or was it the same question here?
Yeah. You need fixes every single class.
No, just as a. Yeah. It was weakening what I was doing.
Sorry.
So I'm enlarging the set. Okay. What about the kernel? Are there automorphisms which induce the identity in homology? Okay? The fact is, the kernel of A has to be contained inside here, and it is finite. How do you see that? So it's the kernel. So F star is the identity. In particular, it is the identity of the Keller cone, which justifies this containment. Okay? For this, you just observe that if it fixes, once it fixes the Keller class, and this really fixes all Keller classes because it induces the identity, okay? It fixes the Riemannian metric which you can associate it to the Keller class. Okay? And now, so here, let me just write quickly like this. So, if F is inside A, then or let me make a weird here. So this is a Riemannian metric. This is known to be compact inside a discrete group, so it's finite. Okay? They are both finite. All right.
I thought you said that before that every element of the automorphism group X preserves a kind of class.
Yes, but as I said, we will come back to that tomorrow. I will
Why doesn't this group already the kind of class which is preserved?
Can you repeat the question, please?
I see. No, I agree. Okay, I see your question. No, I was right before. That's invariant. So the question was if I was right or not about saying it preserves really a Keller class. And that is false. What it has to do is to send the Keller class into a Keller class, which implies this condition. Okay? That's the only correct. Okay? Otherwise, this would work for any automorphism. Thank you. Okay. Now, consider the group character. In yellow or G, we consider the group character alpha long subset So let's take alpha with the group character describing the action of your element of the group on the symplectic form. Okay? What can we say about this group character? So what about the image, first of all? Well, it's finite. So it will be cyclic group. finite. In other words, this M such that alpha G is M. Okay?
Right, sorry, but I think I confused you with my previous question because your argument just shows that the order of such element, an element that preserves the Kähler class, is finite. Yeah, and this argument works just because we can take just one Kähler class for all elements with this property.
Okay. All right. And once we have this, we can consider the sequence. Right? This here is just a kernel of alpha. Sorry, maybe since they are not abelian groups, then it's better if we use one. All right. Now some definitions. I will probably maybe I can sketch the proof. I can get to the proof I want. But I should go up. Definition. If alpha G is equal to 1 for an element of our group, we say that G is symplectic. Simply because it's preserving the symplectic. Okay, I don't think the definition has to be justified. If not, G is not symplectic. And we say that it is, and it is purely non symplectic. Over the D, if alpha G is the primitive root is primitive. Okay. If G coincides with G0, we say that G acts symplectically. So null group, right? These are single elements of the group. Here you have the whole group. And how many minutes there are? 2, 3 should be okay. See, at least 2 stages. Then we'll see how much we can prove. The proposition by Boville that I wanted to recall. So it's Boville and Nikulin, in fact. It's Nikulin, concave free surfaces, and then Boville for irreducible holomorphic symplectic manifolds is following. So if X is not projective, equal to 1, and the action of your group is symplectic. Okay? In other words, you can have no symplectic actions only on projective, irreducible or lattice-theoretical. Okay? And second is that the Euler function of your M, which was the order obtained as the image of G, has to be more or equal of the second Betti number times the Picard rank of your X. In the last minute, I should at least have the time to prove 1, and we'll resume tomorrow with the proof of 2. Okay?
Does the first statement mean that there are no automorphisms of X at all? Does the first statement mean that there are no automorphisms of X at all?
An automorphism, if there is any automorphism, I'm not claiming back. If there is such a group action, then it satisfies that problem.
So it means that there are no automorphisms of finite order.
No.
But if you write that M is equal to 1.
Yes. Which means that there are no automorphism of finite order not preserving the symplectic form. M is the order of the image of alpha, which is the character of the action on each to 0. Okay? Everything which is alpha n equal to 1 means that everything is forced to be symplectic. Okay? But there can be symplectic automorphisms. Okay? Okay. I forgot to. And I think I should stop here, so maybe I'll start with the proof tomorrow.